So now the big question is, how many different ways can this get arranged? And I'm hoping that sounds familiar to you guys. So let's think back to what we did back in the AAT. So let's say I've got 10 people lining up in a line, or in this case, n people lining up. How many different ways can they line up? Well, how many ways can, let's say we have those 10. How many people can stand in the front line? 10 different people can stand there. However, how many people can stand in the second spot? Well, only 9, right? Because one of them is standing in the first spot. And then how many people can stand in the third spot? Well, 8, because you got one person standing in the first spot, you got one person standing in the second spot. So if you have 10 people you're going to line up, and they're all different, and order matters, that would just be our 10 factorial. Hoping you guys remember that from back in the day. Now the question is, when you saw this before, some of them, like between the states and the quarters, if I have state, state, quarter, 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 okay, sure, that's a lowercase q for some reason, quarter. If I rearrange these two states, it doesn't really matter too much. So that was called a combination, right? First one's a state, second one's a state. Doesn't matter if this happens to be the green state quarter and this ends up being a pink state quarter, because they're all just quarters, right? So when we look at this, since this switching around of any of these S's or any of these Q's don't matter, this is what we know as a combination. If it mattered, if like this quarter and this quarter switch mattered, then that would be a permutation. So I think you guys remember there was a big thing about grouping. How many ways can you group things? If order matters, that was a permutation. If order doesn't matter, that's a combination, which was that whole NCR thing that you guys did in the AT. Let's think about why does that work and how, like, what do you have to do? So one of the ways I think about this, if I wanted to do 5 choose 2, is I have 5 things that I want to arrange, and there is 5 factorial ways. However, I don't really care about 2 of them, so those 2 states, they can flip around. So those 2 can be in any order, and there's 2 factorial ways you can put them in any order. And these 3 Q's, they also don't matter. So since these 2 don't matter, the other 3 don't matter as well. So 5 choose 2 would be this. If I had 27 and I wanted to choose, let's say, 8 of them, this would be, I have 27 things that I can line up any which way, and I don't care about how those 8 are ordered, but then I also have another 15 that I also don't care about how those are kind of rearranged within themselves. So this is our formula. So you know in the calculator how to do this, or you were at least one time in your mathematical life told how to find this in the calculator. But that's what the formula is. Now, a little bit more straightforward is on the next page. So if you're looking for the mathematical version of that, we'll flip our page over and take a look at what they are. So these are the couple different formats that you're going to see this in. So the probability that x is going to be whatever it is. So think about this as like probability of getting 2 state quarters, so x equals 2. And in our case, it would be our 5, because that's what n is in this case, right? 0.5 quarters, choose 2, times the probability that you're going to get a quarter, which was 0.25. And how many state quarters are we going to have? We're going to have 2 of those. And then this would be the probability of not getting a state quarter, which would be 0.75. And we had, well, n, which is 5, minus x, which is 2, so we have 3 of these. This was our probability of getting 2 state quarters, right? Now all we have to toss on here is how many different ways this can happen, and that's our formula. Now the other notation here is actually what the AP tends to use. This is the same thing. This is n choose x. So even though it's written this way, which is kind of a little bit weird version of it, if you look at the rest of the equation, is exactly the same thing. This one at the bottom here is the formula for 5 choose 2 basically written out. So 5, that's my n, x is 2, so here we plug in 5, so it's 5 factorial, over 5 minus x. Sorry, I got interrupted there for a second. Trying to remember for a second, we have a spot. I think we were just filling into this formula to show exactly what everything is. So n was again 5, right? So 5 minus my x, and x in this case is 2. So 5 minus 2 factorial over, and then x, which is 2 factorial. So I think I wrote this the other way around, where I had the 2 factorial first and the 3 factorial second. But because they're just multiplied together, it really doesn't matter. And this part here is still the same. And again, sometimes people write this as q to the n minus x instead of 1 minus b. But this is the way right here, I believe, that you'll see in the orange packets if you go looking for this formula. So again, it's kind of a complicated formula, but just as I said in all of the stuff, it's not so much about memorization, it's about being able to apply this and knowing when you can apply this formula. Alright, so let's try. So the notation using the coordinates example, so I basically did that right here for us. So this will be our notation, but let me move this kind of down the page a little bit as well. Alright. So probability that x equals 2, so the best way would be we have 5, choose 2. And then, so that's how many ways this can happen. And then we have 0.25, and we need this to happen 2 times. We need 2 successes, right? And then how about our failures? So there's 75% chance of failing, and we have to fail 3 times. So this is the ways it can happen. This is the probability of success. This is the probability of failure. You need all of this stuff to happen at the same time, so you've got it. So some of the notation things. X is the number of successes, but you have to state this yourself, okay? You can't just start using probability that x equals 2 and just assume that the AP knows that you know what you're talking about. So you have to tell them that you're going to say, let x equal the number of successes. Binomial notation, that part you can just say this, and they will know whether n comes first and p comes second. Like, you don't have to worry about that. But the calculator keys, you can't use the calculator keys that we haven't really even talked about yet, because different calculators have different keystrokes. So whether you use the TI-83 or the Casio calculators, it's not universal. N is the number of trials, P is the number of successes, probability of success, Q is the probability of failure, but it's also the same thing as 1 minus B, so you don't need another one. N choose K is the number of combinations. N things taking K times K at the time, which is exactly the same thing as this. And choose K. Alright, so pause if you need to go and make sure all your notes are down, and then we'll move on. Alright, so next question here. For a blind multiple choice test, what's the probability that the student will guess exactly 5 questions correctly? Alright, so the first thing is this 2 options? Yes, there are 2 choices, 2 outcomes, sorry. There are successes or failures. Are there a fixed number of trials? There are 10 trials, which is our n. Is the probability of success the same? So yes, P equals 1/4 every single time, and Q equals 3/4. Almost identical to the quarter problem, right? And then, is each trial independent? Yes. Now, the problem wasn't in your actual case. Now, the answers were all going to be independent, but you are not a very good random guesser. The chance that you picked C on the first question probably does influence your probability of picking C on the next problem. However, if it's by multiple choice, each set should be independent of each other. But this was a little bit, it's a little bit suspect because of the fact that one of yours does not influence the other. However, the chances on your answer key, those were randomly selected because I used a random number generator and picked me 10 random numbers between 1 and 4, and those were our letters in our blind guess. So how do we figure out this? What's the probability that x will be 5? Alright, so first thing we have to know is we're going to let x equal the count of successes. And the other thing we have to do is we have to realize that x is binomial, and it has how many trials we have? 10 trials. And our probability of successes is a quarter. Now, you can either write it this way, or write it out in words, based on the words I said out loud, or you can write down the formula. So our formula is we have 10, and we're going to choose 5 of them. And then what's the probability of success? Well, we have 0.25. How many successes we need? We need 5 successes. We have 0.75 chance of failure. And, well, how many failures are there? Well, if there's 5 successes, there are going to be 5 failures, because there's 10 trials. So this will give you the answer. Now, here's the thing. This 10 choose 5, 10 factorial, divided by 5 factorial times 5 factorial. I'm not going to try to figure out what 10 factorial is. I'm also not going to try to figure out what 5 factorial is either. That on its own isn't a large enough number. So even though I'm going to write this way, I'm going to go to my calculator to figure out what the answer is. So we are going to go there next. So in our calculator, this nice pink calculator I got here, you're going to hit second distribution, second vars, and we go to binomial, and I went up to get here, and there's either the binomial PDF or binomial CDF. For PDF, I want you to think point, CDF is cumulative, but I just want to know exactly at 5, so I have to 0.5, and what do I have to tell it? I have to tell it 10, comma, my point, which is 0.25, or I'm thinking NP, per point, for some strange reason, probability 0.25, and how many successes do I want? I want 5 successes. I enter, and I get 0.5839, or 0.05839. Now, if I've got my stat wizard turned on, which I think mine is probably off. Oh, Avery's beeping. I don't even think I have the stat wizard on this calculator, so if you do, then it's a little bit easier to see. The probability that this happens ends up being this 0.5058, so 5.8% chance of success.